Hello everyone. In this tutorial, we will study the SLERP function of a quaternion in Unity, which allows us to transition from an initial orientation to a final one over a specified period of time, performing smooth rotations. In this tutorial, I will assume that you are already familiar with time.deltaTime, which I have covered in a previously published video tutorial. If you are not familiar with time.deltaTime, I highly recommend watching that video before proceeding with this one. This tutorial was recorded using Unity 2022. However, the SLERP function has been available in multiple versions and will likely continue to be available in future releases. Before we go on, I remind you that, as it happens with most of my tutorials, the text version of this video tutorial is available for free download at the link provided in the description. A rotation from orientation A to orientation B and, more generally, an interpolation between value A and value B over a specified period can occur in various ways. The values can follow a linear progression, a spherical progression, or other types of progressions, including customized ones. In the video, I am showing some examples of interpolation, specifically rotating a cube by 90 degrees around its vertical axis. It is a simple example, but it effectively conveys the concept. The rotation time is mapped within the range 0, 1, where at the instant 0 we have the initial value, and at the instant 1 we have the final value. Intermediate values in the range correspond to the values given by the chosen interpolation. In the examples, the cubes all rotate by 90 degrees in 5 seconds. However, at the 4th second of the animation, which corresponds to the moment 0.8 in the range 0, 1, the various cubes will have different orientations because their interpolations are different. When performing rotations, as in our case, spherical interpolation is preferred over linear interpolation because the result is more pleasing. In Unity, spherical interpolation is calculated using the SLERP function. The initial S stands for spherical, while linear interpolation is calculated using the LERP function. The initial L stands for linear. As mentioned earlier, SLERP is part of the quaternion class, which allows specifying orientations and rotations in 3D space using quaternions, a mathematical concept that I will not explain in this tutorial. I will limit myself to saying that they are used to express orientations, and I hope mathematicians will forgive me for this simplification, and to demonstrate how to use the SLERP function. SLERP is used to transition from orientation A to orientation B. It takes 3 parameters: the initial orientation, the target orientation, and the moment within the range 0, 1 at which we want to know the orientation. In other words, the moment at which we want to evaluate the interpolation. SLERP returns a quaternion representing the orientation evaluated at the specified moment. So, when we write quaternion.SLERP A B 0.2, we are asking Unity to retrieve the orientation that the object must have at 1/5 of the rotation needed to transition from orientation A to orientation B, since 0.2 is 1/5 of 1. If we want the animation to last for 1 second, we can use time.deltaTime in update, because the interpolation range from 0 to 1 can be converted into a 1-second animation using time.deltaTime in update, as I showed in the video tutorial on time.deltaTime. On the other hand, to perform the animation over an arbitrary number of seconds, we should divide time.deltaTime by that amount. I will discuss this in more detail soon with a practical example. Most of the time, the initial orientation is the object's orientation, i.e. transform.rotation, since rotation is expressed in quaternions. Calculating the target orientation, for example, adding an angle in degrees to the initial orientation, can be problematic. However, we will also address this soon in the practical example. Well, let's finally move on to a practical example. In the video, I'm showing a scene featuring a 3D model. Specifically, the model consists of 4 elements: the door frame, the 2 door panels, and a handle. Although the pivot point of the door panel with the handle was initially located at the hinges in my original model, allowing the rotation to happen correctly, for some reason Unity has moved it a bit forward. To solve this issue, I had an empty object as a child of the frame and positioned it at one of the hinges of the door panel I want to animate. Then I make the door panel a child of the empty. This new empty object will need a rotation script, which we will create immediately, naming it door opening, for example. In particular, we want the door panel to open on its own at the beginning of the game, rotating 90 degrees around its local vertical axis, which in this case is the z-axis. The initial orientation is given by transform.rotation. For convenience and to make the core more flexible, I also declare a quaternion variable called startRotation and initialize it in start with startRotation equals transform.rotation. The quaternion representing the final orientation must be equal to the initial orientation plus a 90 degree around the local z-axis. But how do we define this rotation in quaternions? The quaternion.Euler function comes to our aid, which takes 3 parameters, the rotation angles in degrees around the 3 x, y, z axes. So we define the quaternion of the rotation to be performed as quaternion rotation to be performed, and initialize it in start with rotation to be performed equals quaternion.Euler 0f 0f 90f. This quaternion represents the orientation to be performed, but it is not yet the final orientation. We need to calculate that by adding this value to the initial orientation. And here comes the tricky part. To add the rotation to be performed to the initial orientation, the 2 quaternions must be multiplied together. So we define the final quaternion as quaternion target rotation and initialize it in start with target rotation equals start rotation times rotation to be performed. Let's move to the update function, which, as a reminder, is invoked at each game frame, and start writing transform.rotation equals quaternion.slurp start rotation target rotation. And we stop here because we have not yet defined a variable for the evaluation time of the interpolation. This variable must start at 0, so we can define and initialize it outside of update with float evaluation equals 0f. Then we can also write it as the third parameter of the quaternion.slurp function. Additionally, since its value must increase at each frame, we write in update evaluation plus equals time.deltaTime. We know that the final evaluation time of the rotation will be 1.0, so this animation will last exactly 1 second, as we are incrementing evaluation by time.deltaTime at each frame. Now, when starting the game, we will notice that the empty rotates around its vertical axis, but the door panel does not open. This is because I initially set this object as static, as I did not expect to animate it and had Unity calculate the global illumination. However, now I want to animate it, so I deselect the static checkbox in its inspector and confirm the operation for the child objects. Starting the game again, this time we will see the door opening with smooth interpolation in 1 second. How we can now define a different animation duration? The answer is quite simple actually. The increment of evaluation at each frame must equal time.deltaTime divided by the animation duration. With only time.deltaTime, the animation lasts 1 second, so to make the animation last, for example, 5 seconds, we will need to increase the evaluation by 1/5 of time.deltaTime at each frame. So let's define a variable, float opening duration equals 5f, because we want the animation to last 5 seconds. Then, update the instruction regarding evaluation in the update method as follows: evaluation plus equals time.deltaTime divided by opening duration. Save the script, return to the Unity editor, and start the game to observe the result. This time, the animation will be performed in 5 seconds. With this practical example, you can see how to use Quaternion.slurp to smoothly interpolate between two orientations in a specific duration. You can adapt the script to different scenarios or objects to achieve smooth rotations and animations in your Unity projects. So, to recap, in this tutorial we covered how to express the rotation to be performed in quaternions, how to obtain the target quaternion given by the starting quaternion multiplied by the rotation to be performed, how to use the slurp function to perform rotations with spherical interpolations with variable duration and constant execution speed, regardless of the frame rate, thanks to time.deltaTime. I hope this tutorial has been helpful to you. See you soon!